Now this here video's for a feller by the name of Star Q.E.D. Now he seems to think he's on a giant ball floating in space spinning around. But I'm here to prove to him that ain't nothing but a bunch of hogwash. Because if that was true, then the stars couldn't move at 15 degrees per hour relative to him. I tried to explain it to him in the comments, but he wasn't bright enough to figure out what I was saying. So I'm gonna have to show him some pictures. So look here now, feller. If this here is a star, and we'll pretend this is the Earth, and I'll explain what this is later. Okay, so this is the ball Earth. This here is a star. Oh, about 900 zillion light years away. Okay, that's how far this is. I mean, it's as farther than you can imagine. And this is the Earth, and we're looking, and um, we're looking up at this star. So if we start here, so this is the Earth that's rotating around. So if you start here, you don't see the star yet. It's like too early in the morning. It's not like sunrise yet. You get to here, you're at sunrise. You can see the star when you look straight ahead. You get to here, you're about 10 o'clock. You kind of look up at an angle, you see the star. You get to here, you're at midday, you got to look straight up to see the star. And as you come around here, now you have to turn back in an opposite direction from when you started here. You were facing this way. Now you're having to turn around and face back the other way to see that star as you come around to here. And now you can see the star still. And you move back around to here where you don't see it anymore all night. You come around. So that looks nice in like a little diagram. And I've seen them where they slice up this pie into like 15 degrees. And you just go, look, there's 15 degrees. That's how it rotates, and everything around you rotates the same way. But that works if you're looking down at a flat circle, like a clock with the arms going around. It doesn't work if you're on the outside of that clock or ball, riding around, looking at one star that appears to be setting and rising and moving at midday. Because as you come around, you're moving towards, across, and away from. And a lot of guys can't grasp that for some reason. And to make that a little simpler, I break it down into a more simple shape, the square. So when you look at it as a square, you see that what's happening is as you let's say you're rotating around the square, you're traveling around the square, starting nighttime would be down here, and then you'd get to morning here. You could see as you come around, you could see the star. So as you're coming up, there's no lateral motion to you. This star is not moving relative to you in any lateral motion from your perspective because you're traveling towards it. When you get to this like maybe 10 o'clock area, from 10 o'clock to 3 o'clock, you're moving across. But in that same time frame from 10 o'clock to 3 o'clock, which would be like 10, 11, 12, 1, 2, 3, 10, 11, 12, 1, 2, 3, 6 hours. So let's say from 6 hours before 10 o'clock would be 4 in the morning. You spent time traveling towards this star. So its motion relative to you isn't very it's not a whole lot as far as lateral motion until you get to this point on the square. Now we're thinking about the square. When you travel from here to here, there's going to be a lot of lateral motion within the same time frame. That's what's key. And then when you get to here, maybe 3 or 4 o'clock, and move back down, I didn't figure all these numbers. I'm just doing it on the fly, man. So I'm trying to do a lot of things at once. I'm drawing, I'm holding the camera, and I'm trying to explain this shit. So and I'm getting some of the times wrong because I didn't really work that part out yet. I'm just doing it on the fly. But from here to here, again, you have very little lateral motion relative to you of this star. But as you come back around here, you don't see it again. So what would happen is, if you're observing that star from here to here, it's not moving a lot within the same time frame. It takes the same time to get from here to here as from here to here. But so during that time you travel from here to here, no lateral movement because you're moving towards it. From here to here, a lot of lateral movement relative to you, and then from here to here, it goes away again. And as you come back around, you don't see it. So same thing on the circle, but it's more there's more of a variety of angles. It's more kind of a great. It's not so extreme like from here to here, no lateral movement, but from here to here, you're traveling not quite straight at it, but at a little bit of an angle like this. But from here to here, you're making more tracks to cause this thing to appear to move laterally relative to you than you are when you come back from here to here, just like on the square. Can you get that? Can you get that through your thick skull there, Q.E.D? No, you're not. No offense, man. No, you're a nice guy. I like your comments. I'm just joking around a little bit. Another guy was getting sensitive when I was making jokes. I think you could take it, but this is a fact, man. You cannot get around this, and I don't know if you really don't get it still, or if you're pretending not to get it for the sake of winning the argument. I hope you're not doing that. I don't want to waste my time. I just want the truth. I don't want to win an argument and know deep down inside I was wrong. I'm honest, man. I really believe this stuff, that we're not on a spinning ball. Because if we were, this star would move. It wouldn't move at a constant 15 degrees per hour. It would move relative to us slower from here to here as we rotate. Then when we get to here, it would go faster. It would speed up. And then from here back down, its speed relative to us would slow down. Same as on the box.